Hi, and welcome to our first lesson with calculus and remote learning. This is my home office slash guest room slash was my wife's walk-in closet at one point in our lives. It's a multi-purpose room. Now, if you have not read the section already, stop and go read the section. If you have read the section, great, you have the vocabulary which we need. We're going to talk about the first derivative and the second derivative. You read already in your textbook what those things do. What we're going to look at is a different way of doing it. It might make more sense. If it doesn't, you're more than welcome to use either one. If at any point today you have questions, post them in the question section or see me during office hours and we'll make something work. Let's look at what we're doing today. Alright, so our aim today is how do we use critical points and points of inflection to sketch functions. Now you've already read the chapter and you might have a couple of questions, but we're going to take it one step at a time. First off, we're going to talk about what the first derivative says about the function. So we've been discussing the first derivative for quite some time, and we know that if f prime is positive, if it's greater than 0, f is increasing, it's going up. If f prime is less than 0 on an interval, f is decreasing. And what you've seen today and what we've seen in the past is that if f prime is equal to 0 on an interval, then we have a max or a min. It doesn't matter if it's a local max or a local min, or a global of either one, but it just means that we have a maximum and we have a minimum. And what we're going to do now is this one. We have this function, we want to figure out where it's decreasing and where it's increasing. We're going to make a number line graph, just like your textbook says, but first we need our critical points. It's not given here. So let's find them. So what we're going to have to do first is find our first derivative. Luckily, this is a really nice power function, easy enough to find. We know that f prime is just going to be, that's going to be 12x to the third. That's going to be minus 12x squared. That's going to be minus 24x. And this disappears. Now, to find where this is equal to 0, a little bit of algebra can be helpful. We're just going to factor it out. 12 goes into all of them. X goes into all of them. If I take 12x out, I'm left with x squared minus x minus 2. Cool. And then if I just do factors and sums, I'm going to see that this is just x minus 2, x plus 1. Because this times that is that, this plus that is that. Cool, easy peasy. I'm trying to find where this is equal to 0. Well, zero product property says I can just set them all equal to each other. So 12x equals 0, x minus 2 equals 0, x plus 1 equals 0. That means x is equal to 0, x is equal to 2, x is equal to negative 1. These are our critical points. Now, it's important to keep in mind that these are not just where it's doing something, but we're worried about the space between them. And that's what we're going to talk about next. So I have my number line graph here. And I've also set up another table over here, representing my 4 intervals. You might be asking, why are there 3 numbers here and 4 intervals here? It's because I'm worried about what's happening between these numbers. I want to know what happens before negative 1, in between negative 1 and 0, in between 0 and 2, and after 2. And the reason I have these up here is these are the 3 factors of my derivative. And I'm just going to choose a test point between these things, plug them into my factors, and see if they give me a positive, a negative, or whatnot. They shouldn't give 0, because if any of these were 0, then the number I've picked is a critical point, and we already found all of our critical points. Well, I'm going to pick a number less than negative 1, let's say negative 2. If I plug a negative into here, I'm going to get a negative. If I plug negative 2 into here, I have negative 2 minus 2, that's negative. If I plug negative 2 into here, I have negative 2 plus 1, still negative. Negative times a negative times a negative is a negative. Let's do this one. Let's say negative a half. Why not? Negative a half, that's going to be negative. Negative a half minus 2, still going to be negative. Negative a half plus 1, well, that's going to be positive. Negative times negative is positive. Let's make that a better positive. Positive times positive is still positive. Our derivative here is positive. Let's pick a number between 0 and 1. Let's say, 0 and 2. Let's say 1. 1 times 12x is positive. 1 minus 2 is negative. 1 plus 1 is positive. So this is just going to be negative. Because positive times negative is negative. Negative times positive is still negative. Let's pick a number greater than 3. Greater than 2, let's say 3. 36, that's a positive. 3 minus 2, that's positive. 3 plus 1, that's positive. That's positive. And we should see this kind of pattern here in a lot of them, where it's switching direction, because that's what our critical points do. They switch direction. So I'm going to use my graph. I'm just going to plug it in. So f prime is negative, then it's positive, then it's negative, then it's positive. Cool. So that was an example about how to find the critical points and what they tell us about the shape of the graph, where it's increasing, where it's decreasing. We're going to take a look at the inflection points now and the second derivative. I'm going to explain why in a second, that we're not just going to continue with our original function, because it's annoying. But you'll see in a second. If you didn't understand the first one, check out some of the supplementary resources we have. Otherwise, moving on. So we're going to take a look at the second derivative now. What does the second derivative tell us about the original function? Well, if the second derivative is positive, the graph is concave upwards. It opens upwards like this. It would catch rainwater. If the second derivative is negative, the graph is concave downwards. Rain couldn't get into here if it was falling from the top of my notebook page. And if it's equal to 0, we have an inflection point. That's where it just changes direction. We're not going to do this with the first example. I found my second derivative here. The issue is this is a really annoying thing to factor out. So what we're going to do is a second example where we use the first derivative and the second, and we see what's going on. We're going to do the whole shebang here. We're going to discuss this curve with respect to concavity, points of inflection, and extrema. We're going to use this to sketch the curve. So that means that I need my first derivative and my second derivative. Well, my first derivative here, that's going to be 4x cubed, that's going to be 12x squared. So 4x cubed minus 12x squared. My second derivative, well, that's going to be 12x squared. Oh, look, wow, that might be something there. Minus 24x. And we've seen before that it helps to factor these out. Well, 4 and x squared goes into both of these. So 4x squared. I'm going to have, well, x minus 3. Here I'm going to see that 12 and x goes into both, so 12x. And I'm going to have, well, x minus 2. This is a really nice example to do it with. Remember, this is going to give us our critical points. This is going to give us our inflection points. So let's do the first derivative first, because it's first. This is going to be equal to 0, and this is going to be equal to 0. Well, this is when we have x is equal to 0. Because if I set this equal to 0, I get 0. This is going to be equal to 0 when x equals 3. Let's do this one. X equals 0. X equals 2. It's totally possible for one x value to be an inflection point and a critical point. That's perfectly fine. Let's figure it out. So I'm going to do my first derivative first with my critical points. I have 3 areas. I have when x is less than 0, when x is between 0 and 3, and when x is greater than 3. You could also write this the other way as well. And when x is less than 0, we got this, then I have y prime. Pick a number less than 0, so negative, negative 1. Well, that's going to be positive, because if I square a negative, I get a positive. That's going to be negative, so this is going to be a negative. Let's pick 1. Well, that's going to be positive. 1 minus that is going to be negative. And then that's going to be negative. Let's pick 4. That's going to be positive. That's going to be positive. So positive. Now let's do this with the second derivative. So I'm going to be using these points now. So I still have x is less than 0. I still have 0 is less than x is less than 2. And I have x is greater than 2. And I'm going to do it for 12x and x minus 2. I'm trying to find y double prime. A number less than 0, let's do -1. That's going to be a negative. That's going to be a negative. That's going to be a positive. Let's pick 1. That's going to be a positive. 1 minus 2 is a negative. That's a negative. Let's pick 3. So that's going to be a positive. 3 minus that's a positive. This is going to be a positive. So remember, where that first derivative is positive, the graph is increasing. Where that first derivative is negative, the graph is decreasing. For the second derivative, when it's positive, the graph is concave up. When it's negative, the graph is concave down. We don't have to worry about where it's equal to 0 because we already found those for our critical points and our inflection points. Let's graph it out. So I know that I need to figure out some points. I have x equals 0, I have x equals 2, I have x equals 3. To figure out my points, I'm just going to plug into here. And I'm going to get all my important information. Well, if x is equal to 0, that means I get the point 0, 0. If I plug 0 into here, I get 0. If I have x is equal to 2, I get the point 2, negative 16. If you don't believe me, plug it in. X equals 3, well I get the point 3, negative 27 again. Okay, so what I'm going to do is I'm going to first redraw, because I messed up the other two. I'm going to draw a rough sketch with my pencil, using the first derivative information and my critical points. So I know that this is decreasing from negative infinity through 0, through this, and at 3 it's going to turn around and start going up. We know that this is a power function, it has curves to it, so we're going to add in those curves. The second derivative says that it's concave up from here to 0, it's concave down from 0 to 2, then it's concave up again from 2 onward. So, using my concave up portion, this can be concave up. Then I know from 0 to 2, it's concave down, so it's going to go concave down. Then it's going to be concave up again. It has to go through the point, that's okay. Boom. Now we have our graph. Okay, so you saw that example. What you're going to do now are the Q questions in this section and the first 10. If you have any questions, post them in the question section here, or find me during office hours. You can also take a look at some of the Khan Academy materials I'll be posting. He might explain it a bit more clear than I did. Other than that, hope you're all staying safe, and, well, we'll talk soon. Have a good one.